All right, hello everyone, and welcome to my channel. This is an educational channel, and we take a look at great theories of everything from the past, ancient and modern, and examine them closely to help us determine how to use them in our own lives to shift our paradigms, to uh, awaken to 5D consciousness, to form a holistic worldview. And today is our 516th video that we've done on the reciprocal system of theory, originated by Dewey Bernard Larson. And Mr. Larson was an American engineer who lived in the 20th century and died in 1990. He articulated his two fundamental postulates in 1959 about how he believed the universe operated. And then from those postulates derived a theoretical universe, what his universe would look like if his postulates were correct. And then compared that theoretical universe with the empirical measured universe of the modern scientists that they have, assembled in their laboratories and compiled in their tables. We're looking at the results of one of those studies today called Basic Properties of Matter, which is primarily about chemistry. And we are moving on to the end of chapter 24 on isotopes and about to start chapter 25 on radioactivity. So I think I was cut off by time a little bit last episode. So I'm going to back up about a paragraph and try to get through this last stuff here on isotopes and then get into the start of the chapter on radioactivity. Now, if you'd like to get a fairly thorough rundown on how the postulates of Larson and how he derives his theoretical universe and what those ramifications are, you want to watch one of my first 474 videos on this topic. For now, I'm just more or less assuming that you have some kind of background or some kind of understanding of the reciprocal system, or that you are not afraid of the unknown and have no problem wading into unfamiliar territory. Catch one of my first 474 videos and then come back and watch this. Or just wing it. Okay, chapter 24, 3/4 or more of the way through. The width of the zone of stability is quite variable, ranging from 0 for technetium and promethium to a little over 10% of the rotational mass. The reasons for the individual differences in this respect are not yet clear. One of the interesting and probably significant points in this connection is that the odd-numbered elements generally have narrower stability limits than the even-numbered elements. This and other factors affecting atomic stability will be discussed in chapter 26. Isotopes that are outside the zone of stability undergo spontaneous modifications that have the result of moving the atom into the stable zone. The nature of these processes will be examined in the next chapter. In addition to the limitation on its width, the zone of isotopic stability also has an upper limit due to the restrictions on the total rotation of the atom. It was established in Volume 1 that the maximum effective magnetic rotational displacement is 4 units. The elements of rotational group 4b have magnetic rotational displacements 4-4. By adding rotation in the electric dimension, it is possible to build the total rotation up to 4-4-31, or the equivalent of 5-4-1, corresponding to atomic number 117, without exceeding the overall displacement maximum. But the next step brings the electric rotation up to the equivalent of the next unit of magnetic rotation. The effective magnetic rotation, that is the total less the initial unit, is then 4 units in each magnetic dimension. As explained earlier, a displacement of 4 full magnetic units is equivalent to no displacement at all. Arrival at this point therefore terminates the rotation. The speed displacement reverts to the translational status. Element 118 is thus unstable and will disintegrate promptly if it is formed. All rotational combinations above element 118 or rotational mass 236 are similarly unstable, whereas all elements below 118 are stable at 0 ionization level. At a finite ionization level, the corresponding vibrational mass is added to the rotational mass, and the 236 limit is reached at a lower atomic number. As indicated by Table 35, the equilibrium mass of uranium, atomic number 92, is 238 at the unit ionization level. This exceeds the 236 limit. Uranium and all elements above it in the atomic series are therefore unstable in an environment that is subject to this degree of ionization. The converse is not necessarily true. That is, it does not necessarily follow that all isotopes below the 236 limit are stable if they are within the zone of stability defined by the ratio of vibrational to rotational mass. At the magnetic temperature corresponding to the unit ionization level, most atoms of an aggregate have 1 gravitational charge, but some have none, whereas others may possess 2 charges. The existence of a doubly charged atom has no observable physical consequences other than the added mass, unless the second charge puts the total mass over the 236 limit. In that event, the atom will eventually disintegrate. All of the factors that determine the extent of instability in the elements just below uranium in the atomic series have not yet been identified, but as would be expected, there is a general decrease in the tendency toward instability as the atomic number decreases. The lowest element that could theoretically become unstable by reason of acquisition of 2 gravitational charges is gold, element 79, for which the total mass with 2 units of charge is 238. However, the probability of the second ionization drops rapidly as we move down the atomic series, and while the first few elements below uranium are very unstable, the instability is negligible below bismuth, element 83. As the magnetic ionization level rises, the stability limit decreases still further in terms of atomic number. It should be noted, however, that the rate of decrease slows down quickly. The first stage of ionization reduces the stability limit from 118 to 92, a difference of 26 in atomic number. The second unit of ionization causes a decrease of 13 atomic number units, the third only 8, and so on. All right, that's the end of chapter 24 on isotopes. We're going to start right up here with chapter 25 on radioactivity. The ejection of positive or negative displacement by an atom that becomes unstable for one of the reasons discussed in the preceding pages will be identified as radioactivity or radioactive decay, and the adjective radioactive will be applied to any element or isotope that is in the unstable condition. As brought out in chapter 24, there are two distinct kinds of instability. Those elements whose atomic mass exceeds 236, either in rotational mass alone or in rotational mass plus the vibrational mass added by magnetic ionization, are beyond the overall stability limit and must reduce their respective masses below 236. In a fixed environment, this cannot ordinarily be accomplished by modification of the vibrational mass alone, since the normal ratio of vibrational to rotational mass is determined by the prevailing magnetic ionization level. The radioactivity resulting from this cause therefore involves the actual ejection of mass and the transformation of the element into an element of lower atomic number. The most common process is the ejection of one or more helium atoms or alpha particles and is known as alpha decay. The second type of instability is due to a ratio of vibrational to rotational mass, which is outside the zone of stability. In this case, ejection of mass is not necessary. The required adjustment of the ratio can be accomplished by a process that converts vibrational mass into rotational mass and vice versa, and thereby transforms the unstable isotope into another isotope within or closer to the zone of stability. The most common process of this kind is the emission of a beta particle, an electron or positron, together with a neutrino, and the term beta decay is applied. In this work, the alpha and beta designations will be used in a more general sense. All processes that result from instability due to exceeding the 236 mass limit will be classified as alpha radioactivity, and all processes that modify only the ratio of vibrational mass to rotational mass will be classed as beta radioactivity. If it is necessary to identify the individual processes, such terms as B+ decay, etc., will be employed. The nature of the processes will be specified in terms of the beta particle, and coincident emission of the appropriate neutrino should be understood. In analyzing these processes, which are few in number and relatively simple, the essential requirement is to distinguish clearly between the rotational and vibrational mass. For convenience, we will adopt a notation in the form 6-1, for example, where the first number represents the rotational mass and the second the vibrational mass. The example cited is the mass of the isotope lithium-7. A negative mass space displacement will be indicated by parentheses, as in the expression 4-1, which is the mass of the isotope helium-3. This system is similar to the notation used for the rotational displacement in the different scalar dimensions, but there should be no confusion since one is a 2-number system while the other employs 3 numbers. Radioactive processes generally involve some adjustments of the secondary mass, but these are minor items that have not yet been studied in the context of the reciprocal system of theory. They will not be considered in the present discussion, which will refer only to the primary mass, the principal component of the total. The composition of the motions of a stable isotope can be changed only by external means such as violent contact, absorption of a particle, or magnetic ionization, and the frequency of such changes is related to the nature of the environment rather than to anything inherent in the structure of the isotope itself. An unstable isotope, on the other hand, is capable of moving toward stability on its own initiative by ejecting the appropriate motion or combination of motions. Consequently, each such process has a specific time pattern subject to the probability relations. The basic process of alpha radioactivity is the direct removal of rotational mass. Since each unit of rotational displacement is equal to 2 units of mass on the atomic weight scale, the effect of each step in this process is to decrease the rotational mass by 2n units. The rotational combination with n equals 1 is the H2 isotope, which is unstable because its total rotation is above the limit for either a single rotating system or an intermediate type of structure similar to that of the H1 isotope, but is less than 1 double atomic number unit in each of the 2 rotating systems of the atomic structure. This H2 isotope, therefore, tends either to lose displacement and revert to the H1 status, or to add displacement and become a helium atom. The particle ejected in alpha radioactivity is the smallest stable double rotating system in which n equals 2. Emission of this particle, the He4 isotope, with mass components 4-0, results in a change such as, and then he has a little flow chart or whatever, O16 to C12 plus He4, which would be notated as 16-0 to 12-0 plus 4-0. I'm not really understanding that because I thought that the alpha decay was only for 236 mass units. But anyway, maybe he's just using that as an example. Since rotational vibration exists only as a modifier of rotation, there are no separate units of vibrational mass that can be added or subtracted directly in the manner of the alpha particle. But the mass of the compound neutron has the same single atomic weight unit value as the vibrational mass unit, and like the latter, it is a single rotating system from the material standpoint. It is therefore interchangeable with the vibrational mass. In our numerical notation, it can be expressed as 0-1. This equivalence of the neutron mass and the unit of vibrational mass makes it possible to modify isotopes by adding or removing compound neutrons. Thus, we may start with the mass 2 isotope of hydrogen, H2, and by adding a compound neutron, obtain the mass 3 isotope, H3. And that is H2 plus N equals H3. 2-0 plus 0-1 yields 2-1. Beta radioactivity is a conversion process rather than an ordinary addition process. An isotope that is above the zone of stability has one or more units of magnetic displacement, 1/2, 1/2, 0, in the form of rotational vibration, superimposed on units of the magnetic rotation of the atom. These vibrational units are only half the size of the rotational units. Addition of a second half size unit to one of the combinations of unit rotation and unit rotational vibration is therefore required to produce an additional rotational unit. This cannot be accomplished by direct addition, as a rotational unit is not capable of accepting more than one vibrational unit. However, an unstable isotope is subject to influences that cause it to eject displacement. That is what makes it unstable. An isotope above the stability zone ejects a cosmic neutrino, -1/2, -1/2, 1, and an electron, 0-0-1. This ejection is equivalent to addition of displacement, 1/2, 1/2, 0, the addition that is required to convert one of the half-size vibrational units to a rotational unit. Neither of the ejected particles has any effective primary mass. No change in mass therefore takes place in this process, B radioactivity. The original isotope with the rotational mass 2Z and vibrational mass N becomes an isotope with rotational mass 2 the quantity Z+1, that is, an isotope of the next higher element, and vibrational mass N-2. The total mass of the combination of motions remains the same, but 2 units of vibrational mass have been converted to rotational mass, and the combination has moved closer to the zone of stability. If it is still outside that zone, the ejection process is repeated. Where an isotope is below the zone of stability, deficient in vibrational mass, the process described in the foregoing paragraphs is reversed. In this process, B+ radioactivity, a unit of rotational mass is converted to 2 units of vibrational mass by ejection of a material neutrino, 1/2-1/2-1, together with a positron 0-0-1. The isotope of element Z with rotational mass 2Z and vibrational mass N then becomes an isotope of element Z-1 with rotational mass 2 the quantity Z-1 and vibrational mass N+2. These are the basic radioactive processes. The actual course of events in any particular case depends on the initial situation. It may involve only one such event. It may consist of several successive events of the same kind, or a combination of the basic processes may be required to complete the transition to a stable condition. In natural beta radioactivity under terrestrial conditions, a single beta emission is usually sufficient, as the unstable isotopes are seldom very far outside the zone of beta stability. However, under some other environmental conditions, the amount of radioactivity required in order to attain beta stability is very substantial, as we will see in Volume 3. In natural alpha radioactivity, the mass that must be ejected may amount to the equivalent of several alpha particles, even in the terrestrial environment. The loss of this rotational mass necessitates beta emission to restore the equilibrium between rotational and vibrational mass. Alpha radioactivity is thus usually a complex process. As an example, we may trace the steps involved in the radioactive decay of uranium. Beginning with U-238, which is just over the borderline of stability and has the long half-life of 4.5 times 10 to the ninth, 4.5 billion years. The first event is an alpha emission. U-238 to thorium-234 plus hydrogen-4, and that is numerically notated as 184-54 to 180-54 plus 4-0. This puts the vibrational mass outside the zone of stability, and two successive beta events follow promptly, bringing the atom back to another isotope of uranium. So the thorium-234 then transforms to Pa, maybe palladium, don't know. And that is a 180-54 to 182-52. And then that Pa-234 then becomes U-234, 182-52 to 184-50. Two successive alpha emissions now take place with a considerable delay between stages, as both U-234 and the intermediate product thorium-230 have relatively long half-lives. These two events bring the atomic structure to that of radium, the prototype of the radioactive elements. So then we go from U-234 to thorium-230 by means of, you add He4, so 184-50 to 180-50 plus 4-0. And then from thorium-230, you get to radium-226 plus He4, 180-50 to 176-50 plus 4-0. After another somewhat shorter time interval, a rapid succession of decay events begins. Half-life periods in this phase of the decay range from days down to as low as seconds. 3 more alpha emissions start the sequence. So here we go from radium 226 to radon 222 plus He4, 176-50 to 172-50 plus 4-0, and then that radon 222 to polonium, I think, 218 plus He4, 172-50 to 168-50 plus 4-0, and then polonium to lead 214, PO218 to PB214 plus He4 is 168-50 to 164-50 plus 4-0. By this time, the vibrational mass of 50 units is well above the zone of stability, the center of which is theoretically 43 units at this point. The next event is therefore a beta emission, and that goes from lead-214 to bismuth-214, 184-50 to 186-48. This isotope is still above the stable zone and another beta emission is in order, but a further alpha emission is also imminent, and which I don't understand, because it looks like we're at 234, I guess, if there's a double charge. Okay, but a further alpha emission is also imminent, and the next step may take either direction. In either case, the emission is followed by one of the alternate kind, and the net result of the two events is the same regardless of which step is taken first. We may therefore regard this as a double decay. And we go from bismuth 214 to lead 210 plus He4. It's 186-48 to 166-48 to 164-46 plus 4-0. After some delay due to a 22-year half-life of lead 210, two successive beta emissions and one alpha event occur. And that is lead 210 to bismuth 210, then bismuth 210 to polonium 210, and then polonium 210 to lead 206 plus He4. The lead isotope Pb206 is within the stability limits both with respect to total mass, alpha, and with respect to the ratio of vibrational to rotational mass, beta. The radioactivity therefore ends at this point. I certainly could have used a little bit more explanation there, but maybe you get the point. The unstable isotopes that are responsible for natural beta radioactivity in the terrestrial environment originate either as byproducts of alpha radioactivity or as a result of atomic transformations. Atomic transformations originated by high energy processes, such as those initiated by incoming cosmic rays. Alpha radioactivity is mainly the result of past or present inflow of material from regions where the magnetic ionization level is below that of the local environment. Okay, we're going to leave it there for today and finish up this chapter tomorrow, I believe, and then move on to the next chapter after that, which we're getting right toward the end of this book here. So thanks for tuning in.